Good morning. My name is Melchior Aelmans. I'm with Juniper. I'm part of the service provider architecture team. And before I start, I want to say it's really awesome to be here again. The last time in 2020, I was already at Schiphol airport when Natalie and the PC reached out to me and said, please go back home because the pandemic has officially started. So it's really cool to be here in person again and see you all. One of my interests in Juniper is that I'm part of a study group that looks into quantum technology. For full disclosure and transparency, I'm not a physicist myself, so I don't know anything about quantum. So don't ask too many hard questions about that. But what we're trying to do is to see how can we use quantum technology for networking. One of the, well, let's say, worries or things we've all been trying to be afraid of, or at least what we should be afraid of, apparently, is that at one point a quantum computer will be powerful enough to crack all our security, right? That's the big worry. But a quantum can also bring a lot to our current security protocols and mechanisms we're using. The good thing is that so far we know we're still safe. One of the questions that always comes up is when is this quantum computer powerful enough? I don't know. It could be 5 years, could be 10 years, could be never, because we're still far from an actual quantum computer that is able to factor our public key infrastructure, or at least try to break it. So, but I think, and what we've seen from conversations with, for example, customers and others, is that this is a good moment to start building some knowledge in the subject. So that's what we're trying to do in our study group, and I figured I'd share some of the findings so far, and where you could start if this is a subject that is of interest to you. So the big worry, as we already said, is that at one point a quantum computer becomes so powerful that it can crack our current security and especially PKI, public key infrastructure, or public key cryptography. And as you can see in the diagram, it doesn't really matter if the quantum computer becomes available, how long the key is that you're going to use. It's relatively simple for a quantum computer to factor that key, whereas for a classical computer that is obviously much harder. So what is actually the issue we're talking about? This is probably something that looks pretty familiar to many of you. You're using probably something like AES-256 based MACsec to secure links, or you're using IPsec or any other encrypted tunneling protocol. And that on itself is considered to be quite safe, right? AES-256 is for now considered to be quantum resistant. However, the way the key material is distributed, that is what is vulnerable for the so-called Shor's algorithm. That's an algorithm that runs on a quantum computer and is able to factor that key. So the challenge here is that the public key cryptography is the vulnerable part. For AES, it's fairly simple. If at one point either a classical computer or a quantum computer is able to factor that key, you sort of simply, as far as it's simple, double the key size, and you're safe for quite some more time. Obviously, what is one of the fears is that so-called store and decrypt later attacks could be possible, right? There's rumors that there are big parties or countries that store data until the time that they're able to actually factor that key and so decrypt that data. So it's already, in that sense, could be something to start thinking about. And as I said, AES-256 currently has no vulnerability known, at least by quantum computers. So why is today's key distribution based on PKI vulnerable? You see on the left side you have a key source, that's probably a router or a firewall, that has a random number generator in it. It generates a key, and it uses a mechanism to distribute that key to the other side. Where the risk here obviously is that the key is sent, it's encrypted obviously, but the key is sent over a connection and the key is known at the source and the destination. Obviously the last you cannot really prevent because you need to know the key. But there are ways, and we'll look into that later in the presentation, to distribute that key without it actually sending it over the link. Yeah, so the issue is the key is in full, in some form transported over a data channel, and that can obviously be then intercepted. So what could, or how could quantum technology help in that sense? Let's look at where to place all encryption methods in a diagram. So on the right side you see AES, which is algorithmic strong, so it's considered to be safe. On the left side you see RSA, Diffie-Hellman, which are weaker in that sense and are potentially vulnerable to this Shor's algorithm. Why is AES safe? Because it's a symmetric algorithm, right? You don't need for AES itself to do a key distribution. You need keys, but for AES you don't have to distribute them, or at least not per se using Diffie-Hellman, for example. So Diffie-Hellman RSA, vulnerable to a potential quantum computer attack. And then there's PQC. You probably heard about it. There's lots of discussions going on in NIST, for example. What is a post-quantum encryption mechanism that is considered to be safe? There have been some, well, preliminary positive results. However, NIST later came back, so there isn't really a PQC yet. But the idea is that a post-quantum encryption protocol is not based on using quantum physics itself, but it's still an algorithmic protocol. But it's using more complex forms of, for example, elliptic curve, etc. So that is considered to be safer than using RSA or Diffie-Hellman. At one point, you could foresee that those might not be resistant against a quantum attack either. So there is something invented which is called quantum key distribution. I'll go into how quantum key distribution works later on. But basically you can use that to replace RSA and Diffie-Hellman in order to distribute key material. And now if you combine quantum key distribution with an AES-based protocol, like MACsec, for example, it is considered to be quantum safe. There's lots of challenges with QKD. There's lots of discussion in if QKD is as safe as it is. But it's one of the currently available mechanisms you can buy from Toshiba, ID Quantique, and many others. This is if you are already worried about key distribution at the moment. So what is this whole quantum thing? Again, I'm not a physicist, so I won't go too deep, but there's a few, let's say, basic aspects we need to get a few of the language we need to go into before we, for example, explain quantum key distribution. In our world, as the physicists refer to as classical engineering, so we're that old already, we use bits, right? And a bit is a 0 or 1. In quantum space or in quantum world, they use qubits, quantum bit, which is the mechanical analog of a classical bit, where the big difference is that a qubit can be a 0 and a 1 at the same time. And you only know if it was a 0 or 1 or anything in between if you observe it. The way to sort of understand this mechanism is if you throw a football and you give it a spin, you only know which side you're facing at the moment you catch the ball. Right? If it spins fast enough, you don't see what side you're facing. If you catch it, then you see the logo from the manufacturer, for example. That is sort of in very basic terms how a qubit, once it's measured, you know if it's a 0 or 1. One of the most interesting things of qubits is that you cannot copy them, because if you touch them or if you interact with them, then they already fall back into that 0 or 1 state. So if you send one of these qubits from one device to another, and somebody tries to interfere in the middle with that qubit, then it already collapses in a certain state. So we'll see what that does, but the interesting thing of that is that, as I said, you cannot copy it. It's really hard to interfere or at least try to read what the intended state of the qubit would be in transit. Most of the slides, by the way, have links to either Wikipedia or other pages. So if you're interested in reading more, then I suggest download the slides and you can use the links to read further. The way to bring a qubit, which is an electron or a photon, in our case, in the example, we'll talk about photons. To bring it in that, or to make it a qubit, is to bring it in a superposition. And the superposition is what I just explained with the ball to give it that spin. It goes too deep to explain, really explain how that works, but you use a laser, a pump laser, to give the photon a certain spin. And you can compare that to an audio wave. If you listen to music, you hear certain tones, and these are formed by audio waves, right? And if you combine multiple audio waves, you hear a certain tone, a certain height, etc. But you cannot see if it's a combination of multiple waves. You just hear the result. So that superposition is used to give that qubit a certain spin, and that you can use to transfer data. Then another definition is teleportation, and teleportation is not as we've seen in movies where you can actually teleport somebody to a different location or different dimension. What you do with teleportation is you send that qubit, or if you entangle two qubits, and with entanglement what it does is you have two photons that start behaving in the same manner. Which means if you entangle, or if you bring a photon in superposition, you entangle it with another photon and you take them apart. If you observe the photon on the left side, it collapses, as we just discussed, into 0 or 1. And the photon on the other side will collapse as well at the same time. And that looks completely random until you start measuring that and coordinate. Then you see that the photons on both sides will collapse into the same state. So in other words, there is a connection, sort of, it seems like there's a connection between the photons. That aspect you can use, that's called teleportation, to obviously transport data, or in quantum key distribution, use that phenomenon to create, for example, key material. So in short, classical bits can be 0, 1, qubits can be 0, 1, or anything in between until you measure them, until you observe them. You can use teleportation to sort of transport data, or at least have two photons collapse into the same state at the same time. And as I said, one of the most interesting interesting facts about a photon is that you cannot copy it. So that makes it really a nice feature for security, for example. Then going back to post-quantum cryptography, we quickly touched on it already. Post-quantum cryptography is based on the same mechanism as PKI. So you have a key source at one side, which is probably a router or a firewall or some device that wants to initiate a secure tunnel, IPsec for example, to the other side, that generates a key, uses a key distribution mechanism to send that key to the other side. And obviously the other side can then use that key to secure the connection. However, it is still a classical way of sending key materials. So for now, again, there's lots of discussion still in NIST, but it is considered to be safe against a quantum computer. But still you can obviously store what is sent over the link and try to defactor that key material later on. So how does a quantum-based mechanism differ from that? We don't send any actual key material over the link. As I just mentioned, we send polarized photons over a link, and that link could be just the dark fibers as we know them, or you can use a satellite. That's called free space communication. And interesting thing is because you only send photons, you don't send a key. You can try to intercept it, but then the photon collapses, so the other side will know that somebody is interfering with the connection. And even if you were able to somehow learn if the photon would have been a 0 or 1, you still cannot use that information. And we'll see later in the presentation why that is. So you still generate a key on one side, and you, or I have to say, you don't generate a key on one side. You use the polarized photons or the outcome of the observation of the polarized photons to generate a key on both sides. So there's no key material being sent over the link. So how does it work, quantum key distribution? There are two sites which are called Alice and Bob in this example, as in many security examples. And Alice and Bob are sending photons. Better said, Alice sends polarized photons to Bob. And in order for them to make something useful out of that, two men, Bennett and Bressert, came up with a protocol that is called BB84. It was invented in 1984. And many of the current protocols in use by quantum key distribution mechanisms are either based on BB84 or successors of it. But the easiest to explain how this works is to use BB84. So Alice has a source and is sending photons to Bob. As you can see, the photons are, in this example, represented by arrows. So it could be a polarization upwards or 45 degrees, 90 degrees, etc. It is not exactly in degrees that it's sent, but it's to visualize how that system works. Again, she uses a quantum channel, which could be dark fiber or free space. By the way, one of the limitations currently is that you can only do this over about 100, 120 kilometers, because, as I said, you cannot interact with the photons while they are transported, so you cannot regenerate them or amplify them. So you can use passive DWDM, CWDM systems, but you cannot amplify on the way. So that's one of the biggest practical limitations. Bob receives those photons. He has a photon detector, so he can read or observe what the state of the photon is. So both sides, Alice and Bob, they measure their photon on a what's called a standard basis. So as you can see, again, it's a graphical representation. The filter either passes 0 or 90 degrees or 45 or 135 degree polarized photons. So as you can see, some of the photons, like the first one, will match the filter. The second one won't. The third one will match the filter again. The polarized photons Alice sends are completely random. So she uses a random source to decide what the polarization is. And the random filters are, or the filters are random as well. So both Alice and Bob choose randomly what filter to apply to which photon they receive. Based on that, they do a measurement, and as you can see, again, the first photon matches. The second will give a very random outcome because the polarization didn't match with the filter. And the third one will match again. Now, Alice and Bob will use a classical channel to synchronize the filters they've used. And you might think, a classical channel, yes, that's just IP. But with just a filter, you obviously cannot really do anything, right? It just says, I've used this filter and I've used this filter. But interestingly, if you overlay those filters, then you'll see that in some cases you have a match, like in the first and the third photon. They've both used the same filter, and so the outcome is a match. And now you could already see why, if somebody starts interacting with the photons while they are in transit, there is a certain error rate you can get from here, right? And that error rate in QKD is around 50%. So if somebody on the during the transmission interacts with the photon and it collapses in a different state, then the error rate will increase. So this is why it is considered to be more secure. So going back to this protocol, if you then sift through the examples, you'll see that a key is forming, and in the end, by just sending this string of photons, a key of 0101 has appeared on both sides without them actually sending key material between Alice and Bob. So this is why QKD doesn't transport key material. That's a fundamental thing that is different than by using any a protocol like Diffie-Hellman, for example. Again, you can do this over fiber or free space. Obviously, with free space, you can cover larger distances, but you need satellites. So it's probably a bit tough for many to launch satellites to do this. And this is pretty early stage, as I said. One of the challenges is that you can only span a distance of about 120 kilometers. So within a metro, this could work. Within Copenhagen, you could probably deploy this. But if you want to connect to, I don't know, how far is Aarhus away from here? Or Berlin, take an example. That's much farther away, right? So there are challenges. There are also companies building systems like this, but with trusted nodes in between. So with trusted node, it's basically Alice and Bob and another Alice and Bob system with somebody or something in the middle that is considered trusted, because there obviously it is not quantum anymore. But as an intermediate step, you could use a trusted node to span larger distances. Now, coming back, as we already said, one of the things, for example, we've been building proof of concept with, and others as well, is MACsec and IPsec. Those two protocols are obviously widely used, and they are relatively easy to adapt to using key material from different protocols than Diffie-Hellman, for example. You could use, obviously, with the data link larger distances because you can generate the data link. The MACsec and IPsec protocol on itself are just working as we know them. The only way that changes in this case is the way we distribute the key material. But obviously, you can foresee if you cannot transport the key material further than this 120 kilometer. In practice, the link will only be able to span that 120 kilometer as well. But yeah, this is something that many vendors, including Juniper, but also Cisco, for example, have built proof of concepts with. And the QKD solutions, as I said, are already commercially available from a few large companies. So this is something that could work. However, there are, as I said, limitations. So we've tried that. We've built proof of concept, as I said, And the way that works is both, you have two locations, again an Alice and Bob location, and on both locations you put these quantum key distribution devices. It's basically a few U box that fits into your standard 19-inch rack. And you obviously need two routers or firewalls. In between these devices, there's a couple of links. So you have a dedicated quantum channel, again, could be dark fiber. You need a data channel, as we just saw, to exchange these filters between the quantum key distribution devices. And you have your traditional data link between your routers or switches or firewalls. In this case, we tested it with MACsec. And now we need to fetch key material. One of the few things that has already been standardized is the way you fetch key material from a QKD setup, and that is standardized by ETSI. The standard is the ETSI 014 QKD specification. It's just basically a REST API. So the router makes a call to this API, asks for a key and a key ID. The QKD device sends it back. The router installs the key in its configuration or its a database, and the key ID is sent to the other side. You can send that using a classical channel, because with the key ID itself you cannot really do much. And the other router on Bob's side uses that key ID to fetch, using that same REST API, the key from a QKD system. It receives the key back, installs the key, and you have a MACsec secured data link using QKD. There are some things you can discuss. I mean, how safe is it to fetch keys over a REST API, but this is considered to be both in the same location or at least near proximity. So the QKD device is probably sitting next to the router. The way, and things that, for example, have not been standardized are, as I said, ETSI standardized the way you fetch the keys, but what is not standardized yet is, for example, how do you send key IDs between the routers. And there's many more of these findings. So, for example, how long can you wait before you fetch the key from Bob's side after you fetched it from Alice's side? Right? Is that, do you need to fetch it within 1 minute or 10 minutes, or does it store for an hour? How many keys should you buffer, for example? How often, because this system really nicely allows for key rollover, but how often are you going to roll over the key, right? In many cases currently, I don't know how that is in your network, but we see that in many cases keys aren't rolled over that often, even if protocols would allow it. So it's a fairly open question. How often should you do this? You could, one hand, say if you roll over the key more often, it's safer, right? Because if you're able to fetch the key somehow, you only have data for a smaller amount of time. But obviously rolling over keys more often is more load on control plane, and it could lead to more interruptions, because if you roll over every minute and you don't receive a new key within that minute, then what? Should the link go down, or do you have a backup link? So there's a lot of work still to be done in standardization, like IETF, IEEE, ETSI, because there's not one standards organization working on all these different protocols. So before we're there, it's we're still a few years out probably. So that's one of the use cases, quantum key distribution. The other use case where quantum could be handy is to generate random numbers. We use random numbers in everything, right? I mean, if you look at your Linux host, for example, or in your firewall, random numbers are used for many different things. And the way we currently generate random numbers is either by a daemon running on your host, like random or dev random or urandom. And somewhat more complex systems like firewalls, they take into account environmental things like fan speed, voltage, small voltage changes, etc., to create more randomness. However, one of the issues is that many of these random number generators are not as random as we think they are. It's a bit of a theoretical, maybe somewhat fake concept, but you can measure the quality of randomness. And if you look at how in many cases random these sources are, you are probably going, especially for example on VMs, the quality of the random entropy is relatively low, but we rely on randomness for many things. So to come up with a source that creates better random entropy, you could use quantum properties. In this case, again, this is a very simplified example, but you have a light source that produces photons and sends that photons towards a mirror, the green mirror. And that mirror is 50% transparent. On average, about 50% of the photons will bounce off towards photon detector 1, and about 50% of the photons you send to it will be passing through the mirror to photon detector 0. Which photon bounces off and which photon passes through the mirror, that is one of the quantum properties. But if you again would do this over time, you would measure that 50% on average will bounce off and 50% will pass through. You just don't know which photons will bounce off and pass through. So if you do that and you measure the photons that arrive at the detectors, you see that you will end up with a random stream of bits as well. This is what's called quantum random number generator. It's a fairly small chip, and there's already, for example, mobile phones you can buy which have a QRNG chip in them. And this is considered to be a better or higher quality source of random entropy. We try to visualize that, so we took one of, in this case, Juniper PTX routers, and if you look at the top left, figure 1, that is a standard Linux host on a VM running on one of the public cloud providers, and you see that in the middle picture the orange dots are pretty far away on the left side. I don't know if you can see it that well, but from the blue line, and the blue line is considered to be perfectly random. And you see that, for example, if we look at how the PTX does it, it's a little bit better already. The orange dots are closer to the blue lines. The interesting thing is if you skip a few of them and you go to, for example, figure 5, which is a QRNG source on the right side in the middle, you see that that randomness is even better already than what the PTX can generate. And obviously we then try to combine that, and that is figure 6, and you see that we are almost at perfectly random quality. So that is where a QRNG source could help to increase randomness. The question is, it's a bit, as I said, it's a bit of a theoretical discussion, but for example, if you pull enough random entropy from a source, like on your Linux host, the quality of the randomness obviously goes down because the pool cannot generate enough entropy. With a QRNG, the amount of random entropy that is available is much higher as well, so you can pool more randomness. So you can foresee that, for example, in a data center, it could be interesting to have a source generating random entropy for other consumers. So to summarize it somewhat, we identified 3 potential fields of interest to networking. quantum random number generators, as we've just discussed, to increase a randomness that is used by many security protocols, but also for weather prediction models, etc. Quantum key distribution, which has quite a few limitations still, but is already available. And post-quantum cryptography, where we're basically waiting for NIST to come up with what is then an actual safe to use post-quantum cryptography protocol. So then what? Where are we? I mean, what does it lead to? Obviously, the big dream of many folks working in the space is to build a quantum internet. But what is actually a quantum internet? That is probably a good question. The current state we're in is that all these quantum connections we talked about, as you could see in the examples, are always aligned or are currently always next to a data channel. So if you would connect to routers, let's say you have QKD embedded in a router, currently you would still need a separate channel for data and for quantum bits. So the first steps towards a quantum internet is still be having these quantum links adjacent to your data links. Next to the fact that there are still many things you need to solve, like quantum repeaters, so that you can actually amplify quantum signals. Let aside having optics in your routers or switches that can also send and receive data traffic, but could also do something useful with these polarized photons. So on the short term, a quantum internet will always be adjacent to computers or to classical channels. The idea is at one point, if we have repeaters or if we're able to span larger distances with these polarized photons, that you at first will see something appearing like we're familiar with, right? So you will have a transport layer that's just forwarding these polarized photons. And on top of that, there will be protocols next to, for example, QKD that will use those polarized photons to either transport data or do something useful with it. But yeah, I cannot look into the future, but this is probably still pretty far out. I mean, IETF in the Quantum Research Internet Group, there are some drafts being worked on that describe potential use cases for quantum internet. But looking at where we are now, this is at, I would say, 10 years out. There are some test setups being built. For example, as you can see on the right top side, in China, they're building a quantum internet based on these trusted nodes, but they use satellites, so the satellite is the trusted node. And for example, BT in the UK, they're building something like that with trusted nodes in their own data centers, offering QKD to some of their test customers, trying to span also larger distances. And where I'm from in the Netherlands, QTech, which is a part of the university in Delft, is trying to build a quantum network in the Netherlands. So they span multiple locations with dark fiber and trying to build those first steps of a quantum internet. And that was a short introduction to quantum networking. I don't know if there are any questions now. I'll be around today, tomorrow as well. If this is of interest to you, then please let me know. Happy to discuss further. Or if you feel this is something you already want to play around with, we can help you set up a lab or bring you in touch with people. No questions, everybody fall asleep again already.
No questions?
Henrik Krav Petersen from Intembus. I was just asking, I don't know if you can answer, but the quantum key generation, I think, might take a bit longer, since maybe you can get unlucky with the quantum filter distribution, and then there are maybe not many bits to use. Just something I thought about while you were explaining it.
Sorry, you were saying quantum key distribution might take some more time, you were saying? Or?
Yeah, if the filters don't match up, if there are not many bits to use, maybe then the key can be brute forced by the classical way.
Right, yeah, right.
Just something to think about.
Right. Yeah, so the number of photons which are being sent is like millions, right? So the bit rate is yes, relatively slow for data, if you would want to send data across such a link, but for key generation it's quite good. But yeah, if you want to, let's say not per se intercept polarized photons, but you want to just disturb the system, then yes, you could start sending on that fiber polarized photons, and obviously then the error rate will increase, and so the speed of which you can generate keys will drop. Yeah, obviously, yeah. I mean, every system is vulnerable to like attacks, but the interesting thing of QKD is that yes, you can bring it down or mess with it, but still you cannot get the key material just from the polarized photons. Oh, there's a question on the left side. Sorry, Alan.
Getting my exercise up.
Hello. Yes. Hello. I'm down here.
Sorry.
Hello.
Hi.
Yes. So if I have a key where each bit is completely random, then if I have a very long key, I can be sure that the ones and zeros are exactly 50%. So I wouldn't need to try to brute force all ones or all zeros, and I could just try to brute force the keys with high or close to 50% distribution of ones and zeros.
Yeah, but then still, if your key would be 512 bits long, you would still need to try every combination, because every bit in that key could be a 0 or 1. But yeah, in theory, if it's perfectly 50%, sorry?
It reduces the number of tries you have to do.
Yeah, but it's not 50% exactly. In theory, perfectly random would be 50%, right? But that you cannot never achieve perfectly 50%. But yeah, probably in theory, I'm not a cryptographer, but it sounds as if you have a point. Yeah.
Thank you. There was a detail I didn't follow. If someone is interfering with, we're creating the shared key and someone's interfering with it, we can detect it. That much I got. But if you interfere with it, is there an attack by which you can figure out the key or no?
No, because if you observe the photon that's being sent, then it already collapses. So, and then the error rate will increase, because you would need to send a new polarized photon to Bob, right? Because else Bob won't have any photons to measure anymore. But the error rate will increase, because you don't know if if it collapses into 0 or 1, if that same photon would have collapsed into 0 and 1 on Alice as well.
So I mean, it's fine if someone is interfering with your connection.
Yeah, on the quantum channel, or even on the data channel, if somebody starts intercepting the filters you've used, that's perfectly fine. Yeah. I mean, if you interfere enough, there probably won't be a usable key anymore in the end. But still, you're not able to get the right key from just interfering with the channel or observing the photons.
Before we take the next question, I'd just like to ask you to please state your name and affiliation before speaking. We have a question in the back. Or not.
So, my name is Alex Sonen, I'm from Finland. So do Alice and Bob take turns in sending the photons?
No,
or it's always in one direction?
Yeah.
Okay.
It's Alice is the source, So she has the pump laser, or it can polarize the photons, and Bob has only a photon detector. You can obviously foresee that if you want to cascade, so to span larger distances, that Bob will either have a separate box next to it that is able to send photons, or has a photon source in the same enclosure and is able to generate polarized photons as well. But it's always Alice, or at least one device sending photons, and the other one having a photon detector and observing the photons.
I think we have time for one more question, if there is one. All right. I would like to thank you very much, Melchior, for coming here. Here's a little present
nice.
For you.
Thank you very much. Oh, chocolate. Nice. Thank you.